Today we're going to continue learning about logarithms. Um, this is from Unit 8, Quiz 2, and we're going to be covering the change of base rule, as well as how to calculate some different equations using natural logarithms. And we're also going to look at some word problems today as well. So for this first problem here, we have a lot going on here. We've got 6 times log base 7, 681. And we have to use the change of base rule in order to solve this. And the change of base rule, when if we rewrite this, we can say this is 6 times, and now we're going to write the logs as a fraction. So this is actually read log base 7, 681. So log base 7, the base, I like to think of the base as something that's at the bottom. So we're going to rewrite this as log base 10. And we're just going to write log 7. And the 10 goes there, but we don't really usually write the 10. It's just log 10, 7. But it is base 10, and that's what our calculator recognizes logs as base 10. And we're going to write log 681 up here. Okay. So now that we have that, we are just going to type this in the calculator, and it wants us to find a rough estimation rounding to the nearest thousandth. So we type this in our calculator. I would say let's type this in one at a time here. So if we type log 681, enter, that's approximately 2.833147. And I'm going out a lot of decimal places because it wants us to go to the nearest thousandth. I'm just going out a few extra to be careful. Log 7 is 0.845098. And then we're just going to divide that. If you're able to go back on your calculator and actually type the exact answer that your calculator gives you, that's going to give you an even more exact value. But this ends up being 6 times 3.352447. And there's more decimal places after that. If your calculator goes out even further than that, that's great. And so looks like I get a final answer of 20.11468. And this wants us to go to the nearest thousand. So that's that decimal place. So we're going to look at the 6. The 6 makes it go up. And so this is going to be equal to the nearest thousand, 20.115. That's just some review on decimals. But the main idea here is that the log base 7, we write it as log base 10 on, we can think of it as the base of our fraction or the denominator of our fraction. That's what helps me to remember this rule. And then the argument of the logarithm gets rewritten at the top. Now, sometimes we want to change it to a different log base, like we want maybe like log base 5 or log base 5. You can do that. That's fine. But usually we want to change everything to log base 10 because our calculator is able to calculate in log base 10. Okay, so that's how you solve that one. Let's see if we can just try one more here. Let me take a screen snip here or a screenshot of the next problem. Same basic idea. This one has a fraction on it. That's going to be the same basic pattern though for this. So there's nothing to multiply out front. This is read out loud. We say this is log base 5, 1 over 1,000. And so now this is going to be log 5 on our denominator. And we start there because that's our base. And then this is log 1 over 1,000. Okay, and we'll type that in our calculator. 1,000 is -3. We get a whole number there. Over log 5 is 0.69897. just going to divide these. And our final answer is negative 4.292. And it goes out a little bit further, 0 to 9, but we're just going to stop at the 2 because we want to go to the nearest thousandth. So negative 4.292 is our final answer for this one. Okay, so that's change of base rule. Okay, and the next one's change of base rule, but it's asking us to kind of go in a different direction with the change of base rule. So this next one says here is a log with base 10 on the top, log base 3, and then log base n is on the bottom. And so it wants us to simplify this logarithm and figure out which of these is equivalent to that. So what we can do is we can rewrite the bottom log on the denominator using the change of base rule. So let's just focus on the denominator for now. Log base n of 3, if we use the change of base rule, is log 3 over log n. So now we've rewritten that in log base 10. Again, we don't write the 10. It's just implied. If there's no base written there, there's a 10. So now log 3 is on our numerator. So we're going to write log 3 on the numerator, and then log 3 over log n. And if you're really good at simplifying these, if this is okay, I understand this very well. That's great. I'm just going to show you the long way of how to solve this. So we want to get rid of this fraction on the denominator. So I would just solve it this way. There's a couple different ways you can solve it, but this is how I would solve it. So 1 over log 3, 1 over log 3. And so what happens here is this is log 3 times 1 is log 3. Then we get log 3 over 3. So that cancels out and it becomes 1. Not 0. Make sure you put a 1 there. And then now this is going to be the same thing. This is 1 over log n. So now we have 1 over log n. So that's the reciprocal of log n. And the reciprocal of the reciprocal is just the original. And so we just get log n. So this one's going to be a log n. Okay. So that's how you do those. The next type of problem is going to tell us a logarithmic equation, and we have to solve for the exponential variable in in the equation using logarithms. And it wants us to answer using log base 10. So it wants us to solve for what t is using log base 10. So the first thing that I like to do when I'm trying to isolate the variable here is I would try to get rid of this 11. So if you do that, we would divide everything by 11. And so that would leave us with 10 to the 5t is equal to 20 over 11. Now, it would take a very, very long time to solve this without logs. You would have to do guess and check for what t is. And it's certainly possible to solve that way, but I would say that would take a very long time. So using logarithms, we can speed up the process and solve it algebraically. So we can take the log of both sides. I believe we covered this in the last section. So if we take the log of both sides, we get log 10 to the 5t is equal to log 20 over 11. Okay, then we're going to use the power rule, and this is going to be 5t. We're bringing the exponent down to the front times log 10 is equal to, and the right side just stays the same, 20 over 11. Okay, now this is log base 10, 10. And if we go back to our log rules from the beginning of our lesson, if we set that equal to x, and we use, I call it the snail rule. It's not really an official way to say what this is, but that's how I remember it. This is the base of our exponent, 10. It wraps around, and then it wraps around kind of like a snail to the argument. So this is 10 to the x is equal to 10. Well, that just, x has to be 1. 10 to the 1 is 10. So anytime the base and the argument is the same, it's going to equal 1. But that's just some review. So now we have 5t times 1 is equal to log 20 over 11. Okay, so now we've just got to divide by 5 to get what t is. So we divide by 5 on both sides. We get log, oops, t is log 20 over 11, all divided by 5. And it wants us to write this as a logarithm base 10. This might be an acceptable way to enter it in. I would suggest, though, writing it like this: 1/5 times log 20 over 11. That's just my suggestion for how to write part 1. Okay, and then it says to approximate the value. That's the second part. So I would solve the log 20 over 11 first, and then just make sure to close those parentheses on your calculator. I think that's probably the most helpful thing to do, just in case. Just close those off. So we get about 0.25963 for what log 20 over 11 is. Then we're going to times that by 1/5 or divide by 5. That's the same thing. And so t is going to be approximately equal to 0.051927. It wants us to go to the nearest thousandth. That's tenths, hundredths, thousandths. So it wants us to go to that decimal place. This is a 9. That means that's going to round that 1 up. So this becomes 0.052. Okay, so that's how to solve for variables when they're given to us as exponents. We want to use logarithms, and we take the log of both sides, and then we use the properties of logarithms to do that. And let me just find the properties of logarithms again. I know we went over these already, but let me just copy paste this. And you can take a screenshot of this if you need to. These are all the logarithmic properties. So we use the power rule for this formula here. And then this is the change of base rule written algebraically as well. And then in the previous videos, we went over the product and the quotient rule as well. Okay, so if you took a screenshot of that, great. The next problem we're going to go over is, let me see here. Next one is another one that's similar to this, but it gives us some multiple choice. So it's basically the same thing using logs, taking a log of both sides, but it gives us a multiple choice. And sometimes we might get an answer where it's a decimal, and we have to match that decimal to a fractional value that it gives us from the multiple choice. So the first thing we're going to do here is we're going to divide by -100. So we get 2 to the 0.5y is equal to -5 over -100. So I just divided by -100 on both sides. Okay, and if we simplify this, this is 2 to the 0.5y is equal to, this becomes a positive value, 0.05. We're going to take the log of both sides. This is now log 2 to the 0.5y is equal to log 0.05. Then we're going to use the power rule. This is 0.5y times log 2 is equal to log 0.05. Then we're going to divide by log 2 on both sides. And we have 0.5y is equal to log 0.05 over log 2. Okay, before we go any further with this, I'm going to change this now with the change of base rule. And so to do that, let's see here. To do that, we're going to go backwards. So we're going to now write this like this as a single log. This is now, we're going to say log base 2 has a base of 2. That's on the denominator. And then the argument is going to stay the same as 0.05. So now we've changed, we've kind of gone backwards using change of base rule. So now the last thing we're going to do is get rid of this 0.5. We can divide by 0.5 or we can multiply by 2. I'm just going to do times 2 and then times 2. So y is equal to 2 log base 2, 0.05. And if we look at our answer choices, it might look at first glance like none of these match, but this one's actually answer choice C because 0.05 is the same thing as 1 over 20. So if you type 1 divided by 20 in your calculator, you'll get 0.05. So y equals 2 log 2, 1 over 20. So that's how you do those. So it's like using the change of base rule, going in the other direction. All right. The last problem that we're going to look at is a word problem. And it's kind of the same thing. It's kind of, we're going to use these same rules, but we have to assess what these different values are in the word problem. So this first problem says Noah borrows $2,000 from his father. He agrees to repay the loan and any interest determined by his father as soon as he has the money. And this gives us an equation. So it gives us the equation for the total amount that Noah is going uh, to pay back his father, which includes the 2,000 that he borrowed plus any interest that he had to pay extra to his father for the time that it took him to pay it back. And so the total amount that Noah paid his father back was $2,450. So he paid his father back 450 extra dollars uh, because it took him some time to pay him back. But that's not quite what the question's asking. The question's asking us to find how much time did it take in years for him to pay back all that money. So the 2,450 is what A is. That's the total amount that he paid. So we're going to write 2,450 is equal to 2,000 e to the 0.1t. Now, the first thing that I like to do, again, is try the very best that I can to isolate the t variable, or the variable we're trying to solve for, in this case, t, using just standard algebraic methods, not using logs, just trying to move everything to one side as much as possible. So the easiest thing to do would be divide by 2,000. So now we're going to simplify. 2,450 divided by 2,000 is 1.225. And that's equal to e to the 0.1t. Now we're going to take the log of both sides, but instead of using the log, we're going to use the natural log. Natural logs, they have the same rules as regular logs, except for their base is e. So the calculator, you can calculate things that are log base 10 very easily. And you can also calculate natural log of e, base e very easily, right? X and X there. So we're going to take the natural log of both sides. The same basic rules apply. So we're going to say ln of 1.225 is equal to ln e to the 0.1 t. Now we're going to use the power rule. And so we're going to write 0.1 t times ln e. Now, the reason that we're using ln for this is because there's an e, and what happens is ln e, we went over earlier that log base 10 of 10 is 1. ln e is also 1. And the reason is if we write ln e equals x, and we do that same snail rule is what I call it. This is the base e to the x is equal to e. And x has to be 1 because e to the 1 is the only way that we would get what e is equal to. So this equals 1. You can either cross it out, or you can say times 1, or you can do both. That's fine. And so this is ln 1.225 is equal to 0.1 t times 1. I'm just going to write times 1. And then we're just going to divide by 0.1 on both sides. And you could get a decimal value for this. I'm going to calculate what that is. But the problem is specifically asking us to write it as a logarithm. So this is technically the final answer that they want us to write it in. But let's just make sense of this just for a moment here. So we'll find what an actual value of this would be. So we calculate ln of 1.225 and then divide that by 0.1. And we get t equals 2.0294. So that's how many years that it took Noah to pay back the $2,450. Okay, so that's everything on logarithms and natural logs. We haven't really gone over much graphing stuff yet, but I think that's okay. Um, Definitely check out some of the reading on logs as well. And I can certainly address any questions that you might have regarding logarithms also.